Welcome to episode 2 of our glass defects series. Today we focus on reams, a major cause of optical distortion in glass. A ream is a manifestation of compositional inhomogeneity in glass. The compositional variation creates a local refractive index variation, causing light to bend differently as it passes through the glass. As a result, the defect appears as a visible, broad, wavy region within the glass. Reams are usually associated with large-scale compositional disturbances. Common causes include raw material variability, silo charging errors, batch segregation, weighing errors, poor batch mixing, and inadequate furnace convection. These conditions can prevent complete homogenization of the melt and led to broad refractive index variations in the finished glass. How does compositional inhomogeneity develop into a ream? During melting, furnace convection currents continuously stretch, fold, and disperse the original compositional disturbance. As the affected volume grows and the inhomogeneity spreads throughout the melt, the disturbance develops into a ream. Reams are characterized by a broad appearance, wavy or folded geometry, and moderate to strong contrast with the surrounding glass, and one dominant or several broad bands. These characteristics reflect the evolution history of the original disturbance into a ream as it was stretched, folded, and dispersed by furnace convection currents. A ream becomes visible because its composition differs from that of the surrounding glass, giving it a slightly different refractive index. This refractive index difference causes light to bend and scatter differently as it passes through the affected region. The result is optical distortion, reduced visual quality, and an increased risk of product rejection. Every defect contains clues about its origin. The objective of defect analysis is to move systematically from observation to understanding. The defect reveals characteristics, the characteristics provide clues, and the clues guide us toward the source of the defect. The appearance, pattern, location, frequency, and composition of reams often provide valuable clues about the nature and origin of the underlying inhomogeneity. By analyzing these characteristics, we can often trace the defect back to its source and ultimately to its root cause. What might a quality inspector observe when examining a glass product affected by a ream? In the finished glass product, a ream typically appears as a large, continuous region of optical disturbance. Its broad, wavy geometry and diffuse boundaries indicate that the original disturbance has been stretched, folded, and dispersed throughout the melt. The zebra test pattern is one of the most effective methods for evaluating the severity of a ream. The arrows highlight the optical distortion zone within the glass pane. The smooth and continuous bending of the zebra lines indicates a broad refractive index variation caused by a distributed compositional inhomogeneity. The greater the deviation of the zebra lines, the greater the optical distortion produced by the ream, and the more severe the underlying chemical inhomogeneity. The polarized light image reveals the characteristic geometry of a ream. A severe compositional disturbance, repeatedly stretched and folded by furnace convection currents, produces a complex pattern containing thousands of layered flow structures. Like strands of hair deformed by the wind, these layers record the deformation history of the disturbance as it traveled through the melt. Even within this small observation window, the pattern shows how the disturbance resisted diffusion and homogenization despite intense convection. The striagram acts as a historical record of the inhomogeneity. Its geometry reveals the journey of the disturbance through the furnace. Its contrast indicates the intensity of the compositional inhomogeneity, and its homogenization behavior reflects the persistence of the disturbance and how effectively the melt homogenized before reaching the finished glass. In the next episode, we will learn how to interpret a striagram systematically. We will move from observation to interpretation, develop root cause hypotheses, and identify the investigations needed to confirm the diagnosis by prioritizing primary and secondary actions. This video is part of the Glass Defects from Observation to Root Cause series. developed by Lean Technique. Explore more resources and tools at glass.leantechnique.com. Thank you for watching and see you in the next episode of the Glass Defects series.